Hello and welcome to helpyourmath.com. In this video, we're going to look at combinations, which is a type of counting. Before we get to combinations, make sure that you're familiar with factorials and permutations. And you should be able to find those videos somewhere on the screen because they directly relate to combinations. Okay, so a combination. This is a selection of objects when order doesn't matter. So that's the big difference between a combination and a permutation. Order doesn't matter for combinations, order does matter for permutations. Examples of combinations include a selection to a committee, cards in a poker hand, or who you invite to your graduation party, and many, many other possibilities, right? It doesn't matter if you're selected to a committee, you're either selected or you're not. It doesn't matter if you were selected first, second, third, whatever. Cards in a poker hand doesn't matter if you're dealt it first, second, third, fourth, or fifth. You either have it in your hand or you don't. So you can see here, that's what it means when order doesn't matter. And same with the graduation party. You're either invited to the graduation party, you made the cut, or you didn't. And those are just a few. So before we get into combinations, let's just compare the difference between permutations and combinations. So if we're given 4 roommates, we want to list the permutations and combinations if I'm selecting 2 of them. So permutations, you might recall the formula for permute 2 would be 4 factorial divided by 4 minus 2 factorial, which would be 4 factorial over, this would be 2 factorial, so that's, oh, sorry, I don't want to write 4 factorial. I want to say 4 times 3 times 2 factorial over 2 factorial. And so we would end up with 12 permutations. And we'll just list those out because that 12 is not that many. So for permutations, order does matter. So Rachel Eve is one potential ordering. Another permutation would be Rachel Allie, Rachel Carol. We could also have Eve chosen first, in which case we would have Eve Rachel, Eve Allie, Eve Carol. Or Allie could be chosen first, Allie Rachel, Allie Eve, Allie Carol. Or Carol could be chosen first. Carol, I don't know why I went to Allie. Carol Rachel, Carol Eve, Carol Allie. So here are the 12 different ways that we could permute 2 people from a group of 4. For combinations here, order doesn't matter. So if Rachel and Eve are chosen, that's it. That's the only possibility with Rachel and Eve. We would not also put Eve and Rachel, that's the same combination. So we would say Rachel Eve, Rachel Allie, Rachel Carol, Eve Allie, Eve Carol, Allie Carol. And here, for combinations, we would have 6 combinations. So we can see we have, in this particular example, we have twice as many permutations as we do combinations, and that's not always the case. It just so happens that that's just the repetition is by 2. Okay, so let's talk about the combination rule. Recall that the number of combinations from the roommate example was exactly half. This is because once 2 roommates are selected, there's only 2 ways to arrange them, Rachel Eve, Eve Rachel. So we would have to divide out that repetition of 2. So the number of combinations of n objects chosen r at a time should be the number of permutations divided by the number of repeats. So this gives us the formula. We say n choose r, that's n choose r, and n choose r is n factorial divided by n minus r factorial. So there you see, there's permutations. But then we need to divide out the repetition, and the repetition is going to be given by r factorial. So we have an extra factor, or factors, in the denominator. So this is read n choose r, and the formula is n factorial divided by n minus r factorial times r factorial, all in the denominator. With the permutations, I generally would just do them by making the list and dealing with it. With combinations, the formula, while it looks complicated, is going to be a lot easier than trying to divide out repetitions later on. So in general, when it comes to combinations, I do use the formula. Let's practice using the formula, and we're going to ignore these numbers. Okay, great. So 8 choose 4, you might recall 8 permute 4 was 8 times 7 times 6 times 5. Here, 8 choose 4 would be 8 factorial over 8 minus 4 factorial times 4 factorial, because this is n and this is r. So this would be 8 factorial over 4 factorial times 4 factorial. What we're going to do, just like I do when I'm simplifying permutations, I'm going to expand the 8 factorial until I get to the bigger one of these. They're the same, so just till I get to a 4 factorial. So 8 times 7 times 6 times 5 times 4 factorial divided by 4 factorial. And then the other one, so one I'm going to leave the factorial, whichever one matches up here. The other one I'm going to expand. So 4 factorial is 4 times 3 times 2 times 1. Then I'm going to simplify, and it should turn out all of these should be whole numbers. So this should cancel. So 4 and 2 are 8, right? 4 times 2 is 8. So I'm going to cross out the 4 and the 2 with the 8. And then 3 goes into 6 twice. So here I'm left with 7 times 2 times 5, which is 70. Very different than 8 permute 4, which was 8 times 7 times 6 times 5. So 8 choose 4 is 70. We want to find 15 choose 3. So plugging this into the formula, that's 15 factorial over 15 minus 3 factorial times 3 factorial. This is 15 factorial over 12 factorial times 3 factorial. So again, what I'm going to do, I'm going to expand 15 factorial until I get to 12 factorial. So 15 times 14 times 13 times 12 factorial. I'm going to keep 12 factorial as is, but I'm going to expand the other one, the 3 factorial, into 3 times 2 times 1. Those will cancel. And then 3 goes into 15 5 times, and 2 goes into 14 7 times. So we end up with 7 times 5 times 13, which would give us 455. So 15 choose 3 is 455. Lastly, 47 choose 5. This would be 47 factorial over 47 minus 5 factorial times 5 factorial. That's 47 factorial over 42 factorial times 5 factorial. I'm going to expand 47 factorial until I get to 42. 45 times 43, 44. 44 times 43 times 42 factorial. I'm going to leave 42 factorial. I definitely don't want to expand that, but I will expand 5 factorial into 5 times 4 times 3 times 2 times 1. So those will cancel. 5 goes into 45 9 times. 4 goes into 44 11 times. 3 goes into 9 3 times. And 2 goes into 46 23 times. So I'm just going to rewrite these. We have 47 times 23 times 3 times 11 times 43. Everything's gone down there in the denominator. Great. So when I do that, 47 choose 5, or 47 times 23 times 3 times 11 times 43. Ooh, another big number, but not nearly as big as the permutations. We have 1, 5, 3, 3, 9, 3, 9, or 1,533,939. Let's look at some examples of applying the combination formula. So as always, I encourage you to pause the video, try these for yourself, and see how you do. Okay, in our first example, how many different ways can 5 cards be selected from a standard deck of 52 cards? So again, this is a combination because order doesn't matter. You have the card in your hand or you don't. So this we would represent with 52 choose 5. And 52 choose 5 would be 52 factorial divided by 52 minus 5 factorial times 5 factorial, right? Because that's the combination formula. The combination formula is n choose r equals n factorial over n minus r factorial times r factorial. So then 52 minus 5 is 47. So that's 47 factorial. So we would have 52. I'm going to expand this until I get to 47, 50, 49, 48, 47 factorial divided by, I'm going to leave 47 factorial as is, but I'll expand 5 factorial. 5 times 4 times 3 times 2 times 1. So those will cancel, and then I'm just going to cancel the 5 with the 50 would be 10. 4 and 48 would be 12. 3 and 12 would be 4, and 2 and 4 would be 2. I really picked on that 48, didn't I? Leaving us with 52 times 51 times 10 times 49 times 2, which when we multiply that through, gives us 2,598,960. So this means when you're playing five card poker, that's how many different hands are possible. 2,598,960 possible hands. So that's why, you know, certain types of hands are worth so much, because they're very unlikely. Okay, in the next example, if Lily can select 3 friends from 10 friends to take to Six Flags, how many different combinations? So how many different ways can she choose 3 friends out of 10 friends? So this would be 10 choose 3. Plugging into the formula, that would be 10 factorial over 10 minus 3 factorial times 3 factorial. 10 minus 3 is 7, so this would be 7 factorial. So again, I'm going to expand 10 factorial until I get to 7, and then I'm going to leave it as 7 factorial times 7 factorial over 7 factorial, and then I'm going to expand the 3 to 1. So the 7 factorials cancel, 3 goes into 9 3 times, 2 goes into 8 4 times, 10 times 3 times 4 is 120. So there's 120 different ways that Lily could choose 3 friends out of a group of 10. Last one. In a factory, 4 out of every 10 Butterfingers are checked for quality assurance. How many ways can the Butterfingers be chosen? So this would be 100. Out of 100, we're going to choose 4. Ooh, that's a job I want to have. So that would be 100 factorial over 100 minus 4 factorial times 4 factorial. 100 minus 4 is 96. So I'm going to expand 100 factorial to 100 times 99 times 98 times 97 times 96 factorial. And then we're going to leave 96 factorial but expand 4 times 3 times 2 times 1. 96 factorials cancel. 4 will cancel with 100. This would be 25. 3 goes with 99, 33. And 2 goes with 98, and that would be 49. So then we'd be multiplying 25 times 33 times 49 times 97, which when we multiply that through, we get 3,921,225. That's a lot of different ways that we could check for quality assurance to choose 4 out of 100 Butterfingers. These have been examples of combinations. Thank you for stopping by.